Hey, AP Chemsters, this is Mrs. Vanderlei bringing you part 2 of 16.3 of the Blank Wall series. Sorry the last one ended quite abruptly. The bell rang and I had to go. So anyway, where were we? We were at problem number 9. We were trying to determine which acid would be the best buffer for a pH of 4.25, and we determined it was formic acid because, once again, as a little quick review, that if you plus or minus this number by 1, you are in the range of the pH that you are looking for. This one wouldn't have been as good of a choice because it's really at that far end of that range. If you added 1 to nitrous acid, you get 4.34, which is right at this point here. So formic acid is the better acid for the buffer. All right, so we left off and we were trying to find the ratio of the conjugate base over its acid to get this as a pH. Now, before we begin, let's think about this problem. I'm always asking you, does this make sense? And this pH is higher than the pKa. So we want to make sure that this number ends up being bigger than 1. So we're not subtracting, we want to add so we can get 4.25. So how do I get a number bigger than 1? Well, my ratio of base to acid has to be greater than 1. So let's do the math and make sure that what I just said, how I reasoned it through, works with my math, okay? So you're doing algebra. What do you do next? Hopefully you know you have to subtract. So let's subtract each sides by this number, and you should get 0.51 is equal to the log of base over acid. So you're in math class, and you're trying to find what B over A is. What do? Well, what is a log? Log is an exponent. So let's make that 0.51 into an exponent. And then go ahead and solve for that. So what is 10 to the 0.51? And hopefully you got, let's find out here, I'm doing it right now, 10 to the 0.51 is 3.24. Now, did you get that as an answer? Does this make sense? Hopefully you said yes, because doesn't that mean you have more of your base than your acid? Isn't that what 3.24 means? Now, what if you got a number less than 1? That means your base would be less than your acid. Your log would have been a negative term, and your pH would have been less. All right, so let's go ahead and look at problem number 10. It says, which acid in problem number 9 above would you use to create a buffer of 7.35? Well, let's do that first. So again, you need to take the pKa and add or subtract 1 from each of these numbers and see if we can get 7.35. I hope that you see the obvious choice would be hypochlorous acid. If you took plus 1 or minus 1, do you get in the range of 7.35? Yes, you do. All right, so that is indeed the buffer that we need, or the acid that we need. So now what? If you have 500 mils of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt of the conjugate base do you need to make this buffer? Well, we sort of need to go through the same procedure as the last time. So will you pause this and determine at least the ratio of base to acid to answer this question? Go ahead and pause this. All right, so did you get this far? Did you get that ratio? Again, I emphasized not too long ago, what are these values? I just wrote B over A. Maybe I'm getting a little lazy. Perhaps it would make a little more sense if I did this, which truly means the molarity of the base over the molarity of the acid equals 0.65. So now what do I do? Is there any number I can plug into B or A? Well, if you look closely, what do you notice right here? What is the molarity of my acid is 0.1. So if I plug that in here, then I can say, let me go up here, that base molarity of is 0.065. And as we all know, what is molarity equal to? Moles per liter. Well, if I am putting a solid into this solution, I'm going to assume that my volume doesn't change too much. So we're going to negate that. So my volume is still 0.500 molar. So I can do this. I'm sorry, I said molar. I meant liters. So now I can calculate moles of B. So we can do that. 0.065 times 0.5. And now we got to figure this out. Well, what are they asking for? How many moles? No, they're asking for what mass. So how many grams is equal to 0.0325 moles? 1 mole on the bottom. And now I need to put grams on top. So I have a sodium salt. Well, wait. What salt am I using? Let's check this out. I am using hypochlorous acid. I'm using ClO. So if we found the molar mass of NaClO, I can plug that in. Why don't you do that while I do that? So pause this and finish off the problem. All right, I found the molar mass of NaClO is 74.44. I hope you did too. And I multiplied the two together and I got 2.4 grams of sodium hypochlorite. I hope that made sense to you. A couple things about this problem I liked. Once again, let's look up here again. Notice I had to have this term be a negative number. I need to have the log of this number be a negative number so that these two would be equal to each other. And so there it is. So what does that mean? I need to have the molarity of my base less than the molarity of my acid. And look right here, this is what the molarity of my base ended up being, 0.065 molar, which is less than 0.1 molar. So that makes sense. I needed this to be a little bit more acidic to pull a pH lower than the pK, and that's what happened. All right, we're almost done. Let's turn the page. And finally, the last topic is called the buffer capacity. It's the amount of the acid or the base that you can add to a buffer without causing a large change in pH. A buffer capacity increases with increasing absolute concentrations of the buffer components. What the heck does that mean? So as you have higher and higher molarity, that means that it can absorb more acid and base without changing that pH. We kind of learned that in the second part of this problem here, where we had the comparisons of the 0.5 molar solutions to the 0.05 molar solutions. Also, the more concentrated the weak acid and conjugate base that compose the buffer, the higher buffer capacity is what we just said. And then the overall buffer capacity increases the relative concentration of the buffer components become more similar to each other. So again, as the polarities become more equal. So really, the buffer capacity is a combination of the two topics that we started this whole blank wall series in section 16.3 all about, those two terms, the relative abundance and the absolute abundance. Okay, so problem 11, I like this problem. A 1 liter buffer solution contains 0.1 molar of hydrofluoric acid, which we know is a weak acid. It's a strong weak acid, but still a weak acid, and 0.05 molar of NaF. Which action destroys the buffer? Where does this have an issue? Well, first of all, they're not all that close together, so that's going to hurt this. The molarities are not really huge, so that doesn't help either. But let's check this out. If I were to add 0.05 moles of a strong acid, what's going to happen here? Think about it. If I add 0.050 moles of NaF, what would happen there? And if I added 0.05 moles of NaOH, go back and consider the stoichiometry. I'll pause this and think about it while I throw some things up on the board. Remember, we're thinking of stoichiometry. So I chose either A or C to be my issues. I don't think adding a salt is going to make a big deal. What's going to ruin your buffer is if you add a strong acid or a strong base. So which one's going to ruin this particular one? So here, if I add 0.050 moles of H plus, what is it going to react with? It's not going to react with the HF, it's going to react with the F negative. So what's going to happen here? Do you remember what you do with stoichiometry? Okay, let's see here. We're going to subtract 0.050 mole, subtract 0.050 mole, add 0.050 mole. Well, what do you notice is happening? This is a 0, but more importantly, that's a 0. This becomes 0.150. That's not a big deal. Is that the issue over letter C? Let's check this out. Subtract and add. Well, that's 0, but that has happened before. This is not destroyed. I still have 0.050 moles left, and I still have 0.10 moles left. That's not really the issue. The issue is in letter A, where both terms became 0. And so the one that destroys it is indeed letter A. All right, that's it. I hope you learned something, and go ahead and work on some of those problems. Talk to you later. Bye-bye.